or with K&M Technology Group. Here we will have discussions and presentations with technical specialists about topics or problems that are affecting the drilling industry today. We strive to keep the discussion strictly technical, with no sales pitches for products or services. But since we are conducting a technical discussion, for context you should know who we are and what we do. K&M is an engineering consulting firm that specializes in complex and challenging wells. We began with a focus on extended reach wells and have evolved into a company that handles any type of challenging wells, be it unconventional, HPHT, deep water, deep TVD wells, and more. Our highly trained team provides engineering consulting, training and best practices, and field supervision. We also developed ERA, our proprietary torque, drag, hydraulics, and geomechanics software, which makes well planning more accurate and efficient. To learn more, please visit our website at www.kmtechnology.com.
Good morning, good morning, good morning. Good afternoon, good evening, wherever you guys are watching us. I am Mitch Abba Hussein. I'm the drilling engineering manager at K&M. We are bringing another one of these pre-tower with K&Ms. This one's a little bit different than what we've done previously. We have another service provider that's sitting in with us, or manufacturer, I guess. I don't know how you'd classify it.
We would say both. We would say both.
Okay. So service provider / manufacturer. It should be an interesting discussion. So let me introduce everybody that's going to be joining me today. So again, I'm Mitch. I have the esteemed Timothy Boulay, or Tim Boulay, who's sitting in with us also. So go ahead and introduce yourself.
Good morning. Yeah, thank you for having me. I'm excited to be here this morning and learn some new stuff about fancy casing. I've been with K&M since about 2007, so I've seen a lot of changes in the company, and I'm pretty happy with where we're at right now. So.
Thanks, Tim. Lee, why don't you go ahead and introduce yourself?
My name's Lee Pereira. I've been with Tenaris for roughly about 7 years. Recently joined the Well Design Solutions team, where we provide various types of services, including string design assistance, material selection assistance, and even torque drag fatigue assistance. And if necessary, we get involved with failure investigations, depending on what's going on there.
Perfect. Well, thanks for joining us today. And joining us remotely, Jorge, why don't you introduce yourself? Let us know where you're joining from.
Hi, Mitch. Hey, everybody. I'm connecting from overseas. My name is Jorge Cordero. I've been in Tenaris for roughly 15 years now, always working in the research and development part. I've been dealing with connection design in the last few years of my career. And like Lee, I've been doing a little bit of well design and failure analysis. So yeah, that's a little bit of my background in the company.
Excellent. Thank you for joining us. So the topic of discussion today, we're going to focus on Tenaris's wedge thread connection. Some of the latest, I guess, and greatest in the wedge thread development. So I am monitoring the live feed comments. So if you have questions along the way, feel free to chime in with any questions, and we'll try to address them while we're talking. And with that, I'll hand it over to Lee. Lee has a presentation he's going to share with us.
Sure. We're going to go through a couple of slides pretty quick. We should be able to get things going as necessary here. So, trying to get the slides up on the screen.
Hey, it wouldn't be a live broadcast without some technical difficulties.
I can go over the agenda of the presentation. I've got a lot of things memorized over here. We'll kick it off by first discussing the challenges that are specific to unconventional wells. And then we are going to dive into the development of the Wedge 400 series, just kind of detailing some of the steps that we went through in order to ensure that these connections would be able to perform in unconventional wells and meet the expectations of of the operators, as well as meeting the challenges that present themselves. And then we can discuss some failures. I think that's going to be pretty interesting. We've got a couple of statistics that we can go over, and then just kind of wrap everything up with a slide kind of detailing some of the papers that we introduced to the industry recently through a couple of conferences. And then we're open for questions and answers afterwards.
Maybe while we're sorting out the presentation problem, maybe just give us a little bit about the background at Tenaris.
Sure. So Tenaris is a global OCTG supplier. OCTG supplier. And we have locations and mills all around the world to support the various operations that are occurring in let's say, the oil and gas hotspots. We have our own proprietary connections. We have our own proprietary steel grades that we support the industry with. Most of our proprietary products are very tailored towards specific applications. For instance, these Wedge Series 400 connections that we were going to be discussing were tailored specifically for unconventionals. We also have connections that are tailored specifically for high-end applications, let's say deep water, high pressure, high temperature wells, wells drilled in the Gulf of Mexico, where you have specific requirements that you need to meet in order to ensure that the connections would be able to perform under specific conditions. So I think as a whole, Tenaris is a premier OCTG supplier to the oil and gas market.
Okay. I think it's worth mentioning, at least to my knowledge, and correct me if I'm wrong, like the wedge thread is something that is specifically unique to Tenaris. Nobody else produces a wedge thread.
Recently we have seen third parties introduce wedge thread connections, and I believe that's more related to patents starting to end, because the original wedge connections were introduced over 30 years ago. So there are a couple of things involved with that.
Like I would say most premium connections with like a higher torque is just the majority of them is a modified buttress, where it's like a buttress connection with a shoulder or something where you achieve some higher torque. Where the wedge thread connection, you're getting a lot of the torque from the thread interaction itself.
Exactly.
Okay.
Exactly.
All right. Well, I think we sorted out the technical difficulties, so we got the presentation up and running. So I'll let you jump into it.
Okay, so let's kick everything off by taking a look at the challenges that present themselves specifically in unconventional wells, although we see some of these challenges in other applications. We decided to introduce these challenges through a slide that breaks it down through the challenges specific to installation, stimulation, and production. During installation, you're obviously dealing with dogleg severities that can range anywhere from, let's say, 10 up to 20, maybe even more if things go pretty bad out there. And therefore connections are going to have to be able to withstand bending, and if you're having to rotate, withstand fatigue that can be accumulated through rotating through these higher dogleg severities. And then we also have to deal with compression, bending, buckling, and again, if you're rotating, having to deal with torque as a load. As far as stimulation goes, there's
I
also
think, I don't know if that's on Jorge's side. Like I don't know. I hear clicking and stuff moving around, so I don't know which microphone is picking that up.
There we go.
Yep.
Right. So during stimulation, you're having to deal with various loads that are going to be acting on the casing string, and as we'll see later on, this is pretty aggressive or rather pretty demanding for the production casing. And then there are also other challenges that present themselves specifically during production. One thing that comes to mind here is gas sealability as a primary concern, and this is also becoming a trend in certain areas. If we think about the Rockies and what they're doing in terms of regulation and how operators are attempting to manage braided head pressure, we can see that gas sealability is definitely a concern. And along with all of this, you also have to deal with trends that are continuing to develop. one of the trends that we're seeing on our end, I guess basically everybody is seeing, is the drilling of longer laterals. And with the drilling of longer laterals comes the need for higher torque capabilities and casing connections, an understanding of the fatigue resistance of your connections if you're having to rotate to bottom, and if possible, an improved fatigue resistance. One thing that we also think about as a trend that is developing here is the manufacturing mode type of drilling. Now this takes a while to explain, but for the most part, it's basically the movement away from individual wells being drilled to pad drilling. And we're seeing basically everybody, I would say probably 90% of all operators are moving towards pad drilling these cookie cutter wells where they're attempting to gain as many efficiencies from drilling out the wells on these particular pads using the same equipment, same procedures. And if we can contribute to these efficiencies, let's say through improved makeup times, this is something that we would like to offer to the industry. And this is something that we considered in the development of the Wedge 400 series. And then the last point that I have on this particular slide, again, Syllability. It's also a trend starting to develop. It's kind of isolated to the Rockies at the moment, but we believe that in the future, there's a possibility that this might start to creep into the other states of oil and gas operation.
Hey, Lee, when you see the trend from single pad drilling to multi-pad drilling, do you also see a change in the rate or the type of casing failures that occur because of the shallow directional work?
On occasion, I would say that those are probably isolated to the initial drilling stages or period.
Sure.
And once they start understanding what is occurring in these areas, they kind of get a grasp of what to do in order to solve these issues.
Yeah, I think what Tim might be trying to get at is when you go from a single well pad to a multi-well pad. A single well pad, there's really no need to do any shallow directional work. You just drill straight down to your kickoff point, you build, and then you drill your lateral. And then when you start making pads, depending on the well spacing and how deep the wells are, it drives some shallow directional work just from an anti-collision standpoint.
Sure.
And so even though you could have the same lateral length on the slide, you showed a couple things. You showed that the move to pad drilling and then the move to longer laterals also. And even with the same lateral length, when you go from straight down, building and drilling a lateral to doing shallow directional work, that can have some severe impacts on the amount of torque that is required to get your casing down.
And side forces and the fatigue on the casing up shallow, which
Exactly. So those are a couple of things that we like to take a look at when we're supporting an operator with torque and drag planning. You're completely correct that just having some additional directional work introduced to the well will require additional torque because of the side forces, because of the additional effects that we see from this shallow directional work. But for the most part, I think that it's pretty tame unless you have a significant dogleg severity that developed as a result of you drilling this shallow trajectory work. So I think that for the most part, it's not a major contributor to need higher torque connections, but it can be if things get out of hand.
Sure. Okay.
Yeah.
I'll let you continue on.
Oh, and one last thing that I just wanted to note as far as challenges go, I think this is more of a financial challenge than anything. If you're not able to reach bottom, you're definitely going to see a couple of financial losses. If you're thinking about how much time is spent attempting to reach bottom with casing in certain scenarios where we've seen, let's say, 6 hours, 8 hours, sometimes even 24 hours of casing being worked at, let's say, in a range of like 100, 200 feet where they're not really progressing, we consider that non-productive time. You're really not making any traction. You're really not progressing with anything there. And then on top of that, if you happen to reach bottom, or let's assume that you call it short, if you work the casing for an extended period, you can possibly damage casing connections, and therefore have to deal with those issues later on down the road when you're attempting to complete your wells. And then finally, just the general loss of lateral length and production that comes from having to call a well short or run short. We think that these are all things that need to be considered when planning and ensuring that you have enough torque to reach bottom, and just kind of just going through that planning period first to understand what to expect as you're running casing, especially the production casing in these unconventional wells.
Right. So it goes back to the whole systems design concept that, I mean, it's not just getting one piece of equipment or one tubular or something. We have to look at the whole operation and,
exactly.
and be ready to take advantage of this new technology.
Yep. And I think with that, we can start introducing the wedge thread connection and kind of go over the wedge thread profile, which will help us understand what these wedge connections bring to the table.
Yeah, thank you, Lee. I'll take up from here. Well, in this slide, we can see the differences between the dovetail wedge connection and a regular buttress thread. So what we see here is a dovetail wedge shape wrapped around a steel pipe with a given taper, basically. And the mechanism as well the lockup mechanism of the wedge connection that is as follows is in the lower image. So the pin is first stabbed into the box, then we start rotating, and the first areas in contact are the roots and the crests. That's the image in the middle. Then that will increase the torque since we have to overcome some radial interference between the two pieces. Like eventually with more rotation, all the gaps between the threads start to narrow and eventually close, so we can start really see that wedging effect. It's at that moment that really all the surfaces are in contact, the roots with the crests and the flanks. This final position really gives the connection the ability to seal, like the thread sealability, and also the resistance to torque that is very characteristic of the wedge connections, because all the surfaces are in contact. And from this point on, it's really hard to make the connection to move any further. This is different to what happens in a regular buttress thread profile, because most of the energy that is stored in the connection at the time of makeup comes from radial interference mainly, which needs to be fairly high if we want to have let's say an acceptable level of sealability and also torque. And regardless, there will always be gaps between the threads. In this case, the buttress, well, it's easier to rotate the connection if you really try to rotate it a little bit further, it will move, which in turn will overstress the connection, or in this case, the coupling radially.
Rodney, why don't you bring up the cameras, because I do have I need
This one over here.
There we go. No, get her on Jorge. On Lee. Lee's camera.
Oh,
there you go. So
yeah, that's
I heard that these are in short supply. I was teaching a course, and there was somebody from Tenaris, so he gave me one of these. So this is basically, you can see that from a side profile, it's got the dovetail, and then it's a wedge also. So this would be the pin. This would be the box, and you can see that when you start making it up, there's a lot of play. And then as you continue to push it in, eventually it locks up and you're getting full contact across there. That's what the slides were showing.
Yeah.
All right.
All right, now we can start detailing the Wedge 400 series here. We have 4 connections that were recently introduced to the market, starting with the first, let's say the first connection of this family being the Wedge 461, and this is your standard all-purpose wedge connection. that's being used all across the U.S. nowadays since it's been introduced. It does not have a metal-to-metal seal. It's a full-size coupling. The interesting thing with this particular connection is that as you are making it up, you are going to engage the wedge threads in order to achieve, let's say, a significant level of torque. And as you are installing casing and reaching the operating torque of the connection, you can see an engagement of the pins come in contact, and this is just an additional mechanism to allow for additional torque abilities for this particular connection. And then we also introduced the Wedge 441, which is very similar to the 461. The thing that makes this particular connection different is that we developed a coupling that is extremely slim. In fact, the OD of this coupling is comparable to our wedge integral semi-flush connections. So when you see this connection up close and personal, you can see that the coupling is barely above the OD of the pipe body. We also added a strengthening belt that acts as a shoulder, just in case you're needing to reach the operating torque of the connection, also giving you that additional mechanism to be able to withstand additional torque.
What would be the purpose of having a coupling on instead of just having a semi-flush connection?
There's some efficiencies that are gained in manufacturing wise, where we don't necessarily have to send the pipe over to be swedged and go through those additional manufacturing steps. Instead, we can just have couplings produced in parallel as the pipe body is being produced, and basically just buck them together, similar to what we see with API products.
So from a client standpoint, would the advantage is the advantage cost or production time or what?
A little bit of both. In terms of costs, we like to think that we are passing along some of these costs that we gain in terms of efficiencies.
Okay.
But we find that having a coupling, you also gain other benefits. Typically, when you compare, let's say, the fatigue resistance of various connections, threaded and coupled connections tend to have the higher fatigue resistance in comparison to, let's say, the other extreme being a flush connection.
Okay.
And you have some flexibility too, that if you damage or misthread the coupling, you can just get another coupling.
Sure.
And not have to trash that entire joint. So.
Okay.
Sure.
Exactly, yeah. And the other thing as well is that that straightening belt in the middle helps to control the hoop stresses that happen at the very beginning of the thread, which also helps to improve the sealability of such a very, really thin box, I would say.
All right.
Yep. And then we have the 463 connection. It's comparable to the 461, except that we've added a metal-to-metal seal, and in order to provide gas-tight sealability to a very high level. For this particular connection, it also has a shoulder that you can engage with at the higher torque levels. And then we have the 425, which is an integral two-step wedge connection with a metal-to-metal seal at the center of the connection. And all of these connections can let's say you can kind of pull its roots and find that they all used some form of technology from the original Wedge 500 series connections, especially the Wedge 563, which is probably the connection that most if you've used the Wedge connection, you're probably familiar with the Wedge 563 connection. It's been around for a significant amount of time. It's been used all across the world for all kinds of applications, whether it's unconventionals. In fact, we have some operators that are still familiar with it and have not moved or migrated over to let's say one of these 400 series connections, because they understand that the 563 is a pretty good connection, and sometimes it's kind of difficult to, if it's not broke, don't fix it.
Right. Let's talk about the naming structure for a minute, because back when it used to be simple. It used to be pretty simple. No, keep it on this slide for a minute, because I just want to point out the different numbers. So the three different numbers after. So it's a wedge, and then there's three different numbers. It used to be that 5 signified that it was a wedge thread, and then 6 was threaded and coupled. 3 was semi-flush, and 1 was flush, right? And then there was either a 3 or a 1 at the end, with 3 being gas tight and 1 not being gas tight. So it was a pretty simple naming structure.
Sure.
Now I get confused because it's not just the 5 anymore. I believe you have the 6 series also.
Yes.
Now you have the 4 series, and then you have 6, you have 4, you have 2, which didn't exist before. So and then also there's 1, 3, and now a 5 also, which the 5 didn't exist before. So can you just walk us through the naming?
Sure. I don't know. Maybe Jorge wants to take this one.
Sure. Whoever.
Yeah. Yeah, the naming, like you said, in the 500 series was pretty simple. After the 500 series, we deployed the 600 series that really didn't follow the same nomenclature, let's say. So, for instance, 6 is the number of the series. The 1 is still a flush. The 2 is a semi-flush connection. And then we added, because we added features, then we kind of started like coming up with new numbers and new nomenclatures, but really didn't track back to the original S500 nomenclature. Now for series 400, we try to go back to that. So 4 is a semi-premium series for unconventionals, mainly. Then the digit in the middle is close to what would be in the Series 500. So 6 is for thread and coupled connections. Now, in this case, the 2 is for an integral connection, and the 4 is for a thread and coupled but slim line or a slim coupling connection. The digit at the end is 1 for non-gas tight or not with a metal-to-metal seal, and the 3 is for a metal-to-metal seal. Whereas in the 5, it's a connection that has 2 steps with a seal in the middle. That's also a gas type, but the seal is found in the middle between the 2 wedge steps.
Okay. All right.
Are these all similar in terms of makeup time and makeup complexity?
In terms of makeup time, I would think that I would like to say that these connections were designed with the intent of minimizing the amount of time that is required to make up a connection. In fact, we've measured the amount of time that it takes to make up these connections and compared them against, let's say, our own buttress compatible semi-premium connection, TXP, and we found that these connections are saving a significant amount of time on the rig floor. And if you think about the trend towards longer laterals, you're having to make up more pipe, you're spending more time making up casing, and if you can minimize that time, I think it's pretty important.
So that's between the wedge and other ones, but between the different types of connections, are they close, or is there's certain ones that take a little bit longer, or certain ones that are faster than other ones?
I would say the threaded and coupled ones are pretty close to each other, with the 425 being a little bit different. But you still get a pretty good deep stab with the connection, and we try to minimize the amount of turns until final makeup.
Okay.
Yeah, so let's keep going with the slides here. And here we have a comparison of the torque between the various Wedge 400 series connections, comparing it against the Wedge 563 and our TXP, the buttress compatible semi-premium connection. And you can see that in terms of the operating torque, the torque that we ask operators to meet if they're having to go to the limits of the connection prior to reaching some sort of yield point, we can see that there's a significant difference or upgrade even in comparison to the Wedge 563, which is a notorious, let's say, high torque connection. with the 461 demonstrating the highest torque capabilities over here. So if you don't necessarily need a metal-to-metal seal, but you would like to have as much torque to work with, the 461 is an awesome connection for that.
One thing that I don't know if Jorge misspoke or if I misunderstood, but I'm almost positive that he described the 400 series as a semi-premium connection.
Yeah, so we don't necessarily want to compare it to premium connections like what you're seeing in the 600 series. The 600 series is introducing a significant amount of connection technology, which maintains that premium tag. These connections are also premium in that you have, let's say, a significant departure from what would be considered semi-premium in the oil and gas industry, which is typically highlighting only buttress-compatible connections.
Okay.
But these connections kind of play along that line of premium, semi-premium, although you have a premium thread profile and you have premium metal-to-metal seals. We don't necessarily, again, don't want to compare these against our 600 series, which again has all of this additional technology testing that goes into it. So it's kind of a gray area, I would say, more so than anything.
The 563 was like the Lamborghini of connections for a really long time.
Yeah.
So is the 563 now in Tenaris's eye a semi-premium connection?
No. It's still a premium connection. It's still a flagship connection. Again, it's still recognized. We don't. I don't want to say that we don't advertise it as much anymore, but it's still recognized all around the world as a premier connection.
Okay.
Yeah. Let me step in here. The 500 series is like a really, really good connection, and again, well, you don't have to forget this connection was born, if I'm not wrong, like 1986. So, like, it was very good. It proved to be very good, and it has steel profile features and sealability characteristics that make it a premium connection compared to the 400 series. Like, I mean, one might consider comparing 563 versus 463. There are reasons why we cannot go further in torque with the 563 because we would compromise maybe sealability. Whereas with the 463 we can, but there are other things that are better in the 563 compared to the 463. And of course, the manufacturing time and all these things that are already in the connection, and it would be very hard really to I mean, it's been improved. It can be improved already in that connection, but it's still a very premium product.
Just out of curiosity, how long did it take from the time somebody at Tenaris said, let's make a new connection, until you are in full production mode?
Wow, that's a tough question. Yeah, I would say really depends, but say somewhere between 4 to 6 months, probably, maybe more, 8 months. Mm-hmm. Yeah, it takes some time really because I'm gonna go through it a little bit more in detail, but it's really, it's a process, and there's a lot of interaction, especially for a company like ours that is pretty big in terms of manufacturing capabilities, and it involves a lot of logistics. Just to give you an example, we usually design the wedge connections. Not usually, we only design the wedge connections in Houston. Mm-hmm. Now, from there, all the manufacturing part of those is made in Mexico, and the testing sometimes is either being done in Mexico or in Argentina or in Italy. Depends on the testing capacities that we have in each of those locations. So as you can think, like making a piece of metal travel from one country to the other, it's complicated.
Sure.
So yeah, it really changes.
Okay.
Do all the wedge connections, is the dovetail an integral part of it, or Because you can have a wedge without a dovetail. So do all of them include a dovetail?
Yes.
Okay. All right.
Our connections, yes.
Okay.
There are like lead there he mentioned before. There are some other connections from other players that have the wedge effect, but with different profiles, not necessarily a dovetail.
Okay.
So here I'm going to go through a little bit of the design process. So for us, the design process starts with the input we gather from our technical department and their conversations they have with the operators and their requirements. Saying it another way, it's where do they spot there is a gap between what they need and what is available to fulfill those needs. Now with that input, we go straight to the drawing board and start working first on several concepts. Now in the conceptual design phase, we start with like a blank pipe. Let's say we only define the size, the wall thickness, and the steel grade. And from there, we start mixing profiles, the shapes, the tapers, the thread lengths, and all the other features, seals, if they have seals. And then we do all the geometrical and mechanical verifications to make sure that the structural integrity of the joint will comply with what was established at the beginning. To do that, we use the finite element method. That is what you see on the screen. Basically, that is a mathematical approximation to assess the mechanical behavior of a structure subjected to working loads, whatever those loads are. And it is a methodology widely used in all major industries, going, really from anything, from aerospace to toys. It's everything. And of course, oil and gas is not the exception. So what we evaluate with finite element analysis is axial loads, pressure loads, torque loads, and all the combinations between them, and how the connection responds to that. In the picture, you can see an example of an FEA analysis showing the interaction of the pin faces that occur at high torques. In this case, is the Wedge 461. But like, for instance, we also evaluate hoop stresses. Hoop stress is certainly a concern, because especially in environments where like low to moderate concentrations of acidic gases may play a role and could cause cracking, like hydrogen sulfide. So once we finish with all the mechanical computing work and all the design is optimized both geometrically and mechanically, we move on to the physical full-scale testing part. All right, here is an example of what is a test for non-conventionals, for non-conventional connections. So there is not a standard protocol for testing connections used in the shales, like there is, for example, in conventional plays, or for those familiar with the API 5C5 standard. So we came up with our own protocol in, let's say, an attempt to simulate the actual conditions under which the connection will be used, and also trying to mimic the sequence of those conditions. So this full scale testing, the one that you're seeing here, is again a Wedge 461, 5.5, 23 pounds, P110. So the first two portions are installation, like what we would consider as installation loads. So we'll start first with the side A of the connection that is made up to reproduce the conditions of assembly in the mill. Then the side B, we do that to reproduce the conditions of assembly in the field. We also change the doping conditions and between the side A and side B, basically to account for the differences between the manufacturing process that we have inside of the mill and the manual doping procedures that are in the field. The next part we do is 40,000 cycles cycles of loading to introduce some fatigue, in this case to try to imitate the installation of a rotating string in the hole. So for this connection, we have applied an internal pressure to introduce both hoop stresses and certain tensional load. As well, fatigue is known as a phenomena where tension has a preponderant role, let's say. And also we introduced 15 degrees of per 100 feet of the leg severity. So these 40,000 cycles, just to give you an idea, is the same as rotating a string for about 6.5 hours for 100 RPM. So the next part is a simulation of aging of the thread compound. So it is known that an aged, let's say, thread compound is or may have a negative effect on the thread sealability. And as well, we understand that not all wells are completed or hydraulically fractured right after they have been drilled. Sometimes it takes a few weeks or a few months to do that. So really, that aging of the thread compound, we've seen that it really sometimes it does play a role in that. So for this part of the test, we did it at 302 Fahrenheit for about 24 hours, and that's pretty good enough time to impoverish the conditions of the dope. Actually, when you see them, you see a thread after being through this and without, and really it's like powder. It's really bad. After that, we go to the hydraulic fracturing simulation, which in this case consists of 40 cycles. Each cycle lasts 60 minutes, maintaining the pressure in the connection with axial loading and bending. So for this case, we applied a little bit over 13,200 psi and 72,000 pounds of tension and 25 degrees per 100 feet of flexural moment. And this takes the connection very close to the triaxial limit of the connection itself. For this case, we use water as a pressurizing media. And finally, the last part of the evaluation is divided into two syllability tests, which consider pretty much the same conditions. For this case, we use pressurizing media is gas, nitrogen gas. So the first test is done at room temperature. In this case, we'll limit the axial stresses in tension and compression, as you can see in the image of the upper right-hand corner. We apply 6,250 psi of internal pressure and a moment of 25 degrees per 100 feet of dogleg severity. And then we repeat pretty much the same envelope, but at a higher temperature, 275 Fahrenheit. It is not part of this sequence that I just described, but in addition to that, we concluded a liquid sealability test with a graded envelope, which is the blue line on the left-hand graph, and followed by a limit load test on the right-hand graph. Like, for instance, for the limit load test, so basically what we did is we departed from the upper right-hand corner of the gas envelope in quadrant 1, and we started increasing pressure until the connection failed, basically. So you can see the failure in the point marked by a big red X that falls right outside of the von Mises ellipse. So I wanted to mention that this test is for a 461, which is a connection without a metal-to-metal seal. Of course, if a connection with a metal-to-metal seal is going to be tested, the sealability limits are redefined, let's say. Like for instance, for 463, this test would be different. It would follow the same structure, but the sealability with gas would be completely different.
How often how often are these tests
Yeah.
conducted? Is it like once during the development of the connection, or is it once per lot, or once per order, or?
No. During the development phase, we definitely test them. We definitely do some tests, and we validate. So the way this and that's also an important part that you mentioned. So these connections are designed like in families, or more like in ranges of families. Like for instance, a 5.5 connection, a 5.5 461 will be completely interchangeable between a 5.5 17 pounds per foot up to 5.5 26 pounds per foot. So in here, what we evaluate is, because of course resources are limited, we want to validate what is mostly used. Let's say in this case, we would test the 5.5 20 and the 5.5 23, and from there on we can extrapolate to the other sizes. We do the same for 4.5, which is also interchangeable between a certain range, and for 6 and 7 the same. So yeah, to answer your question, we do that only during the development phase.
On the hydraulic fracturing side, where it says 40 cycles, if you were to assume, say, 200 foot between stages, 40 cycles would be an 8,000 foot lateral, which is right now it's pretty common to go up to 10,000 or even above. So if let's say an operator is drilling 10 or 10,000 foot or longer laterals, and they want to test it to more than 40 cycles, say 60 cycles or 80 cycles or whatever, what would that entail?
This would start a discussion internally in order for us to determine whether or not there is, let's say, an opportunity for Tenaris in testing the connection. There have been occasions where an operator has requested testing specific to their application, and at the end of the day, it's just a matter of who's going to pay for that testing. As Jorge commented, these tests are sometimes difficult to schedule with everything that's going on. So we typically plan out which connections are going to be tested in the following budget year, and it's difficult to really just squeeze something in there. But if there's an opportunity there, and there can, we can come to an agreement with the operator, we'll go ahead and test it to whatever requirements they're asking us to.
Another important part of the connection validation is the fatigue testing. So, to give you a very brief overview to what fatigue is, fatigue is it can be thought as the modification of mechanical properties due to repeated stresses or cycles of loads. Because of this phenomena, a mechanical part more often than not fails at stress levels that are far below its static elastic limit. So in the image, we can see a fatigue test frame that we have in one of our labs. So in this frame, we induced actual loads to exert a mean stress. This is because this sample has the ends are capped. And with the help of a rotating eccentric weight that is in one of the ends of the frame, we introduce these cycling stresses acting on the connection. So the connection is found in the middle of a sample. And with this test, what we want to do is we want to study how the nucleation of cracks occur. So if it's because of defects of manufacturing, or it's because of stress concentrators that we haven't seen during the design phase, whatever it can be, we want to study it here. And then how that crack propagates, or how much time it takes to propagate until its failure. So the failure, we can see it in a through-wall crack in the pipe. And also, I would say most importantly, that what we can extract from these tests is that we can build a graphical representation of the response of the connection to cyclic loading, what we call the SN curve. That this curve allows to correlate the level of cyclic stress to the number of cycles we would expect a connection would withstand before failing. This is particularly important because if we want, or if we're doing a well design, then that information is important. Or if we want to select a connection based on certain given conditions that an operator may have in their wells, that's also important. And as well to feed models of torque and drag and fatigue analysis to make sure that we will be always on the safe side. Now, doing all this evaluation in the lab is it's very important, and but it's especially nice because everything is clean and tidy, and you can measure and control. But really, nothing compares and nothing beats reality. So in our case, that reality is the Rig Direct Academy. So this is a facility that we have the chance to have access, and is in Mexico. So what we do there is, we go to the mill because it's right there, and we take stock connections right coming from the mill, and we test them under various conditions. We use tongs, we use CRTs, we change the doping conditions, we use drilling mud as a lubricant instead of dope, or we use low and high RPM or misalignments, or any kind of test that we want to do. So the images on the slide, for instance, were conditions requested by a customer, but these are not situations that we would advise in actual field operations. So what we want to see in the Rig Direct Academy is, how the connection steps, how it makes up, how it breaks out, how it self-aligns, or what are the limits of misalignment it can withstand, if it displays signs of galling or any other issue. And the last bullet of this list is really important, which is the training of our field services personnel. Especially this is relevant when we're deploying new products or products are being released to the market, like in the case of the Series 400. The facility overall is very versatile because we cannot only organize demos for our internal personnel or customers or operators, but we can also perform failure analysis that we cannot do in the lab or any other type of study. So this is very nice to have, really, for connection development.
Yep.
I think there was one question about, I guess, insights or recommendations as far as, so you said you test to low and high RPM dope, different types of doping conditions. What would you consider ideal, I guess, as far as RPM while making it up, types of dope, how to apply
so we have a, let's say, a running manual which defines all of these conditions, the optimal conditions in order to make up these particular connections. And if I recall correctly, and this is I would say typically what you're seeing is a high and a low RPM that we would like for operators to apply. So during the initial turns, prior to really let's say, seeing the higher torque levels, you may be making up the connection somewhere around like 20 RPM, and then you may see a reduction down to 10, 5, depending on the connection. And as far as doping conditions go, you really want to get a good, let's say, a thin layer of dope around it. Nothing like what we see in this image over here, where we decided to just pack on the dope and see how the connection would respond. And fortunately, what we saw is that it's very robust. All of these conditions here. In fact, I was on location at the Rig Direct Academy, and I believe I took some of these photos that we see on this slide. We ended up getting pretty aggressive with the connection just to see how it would respond, and fortunately it did things that were pretty impressive to me. For instance, in the center picture here that we see with the misalignment, we basically moved the CRT over to see if we can have a great distance between, let's say, the centers of the pipe. We stabbed it in, and at first it's leaning a little bit to the side, and we started rotating it with the CRT, and next thing you know, you just see it align itself, and it fell right in and made up appropriately. We have torque turn plots to show that these conditions, although we don't suggest for anybody to operate under these conditions were things that the connections were able to meet in terms of challenges, and again, kind of show that they're pretty robust.
So you don't recommend using a dope bucket that's been out for like the past 3 or 4 rainstorms, and
of course
just taking a glob of it and slapping one side of the pins and hoping that the
Standard
makeup,
oil field procedure.
Yeah, I mean, we do that with drill pipe all the time. It's standard practice.
We've seen it. No, it's again, we have recommendations on how to run pipe, how to make up the various type of connections, and sometimes they vary from connection to connection, if you have a seal, if you don't have a seal, et cetera. But yeah, there's an optimal way of running these connections, and then there's, let's say, conditions that you don't necessarily want to see while making up these connections. But we feel that these 400 series connections are made for the types of operations that we're seeing in the unconventional space. Oh, so it looks like we have a little bit of time here, so I'll go pretty quick through some of these statistics that we recently published, that we gathered in an internal database that was fed through failures that occurred on our pipe, but also failures that occurred on third-party pipe, where operators were willing to share details of the failures that they had, and allowed us to see what were the failure mechanisms when these failures occurred, and obviously if it happened on our pipe, we have pretty good visibility as to what occurred there. But just to give you guys a couple of numbers here, what we found was that about 60% of all failures were occurring on the connection of the casing, and about 40% were occurring on the pipe body. And then we decided to see, when are they occurring? When are these failures occurring? And about 53% of all failures are occurring during stimulation, which is understandable, seeing as that's probably the worst case scenario that the pipe is going to see when you're talking about extremely high pressures, the introduction of cold fluid. So at that point, you would expect to see a failure if things were to go bad, or at least at a higher percentage. Then about 26% occurred during installation. This is at the time of makeup and during running. And then about 20% occurred during production. And then if we attempt to understand what was the cause, we find that about 31 to 32% was a result of cracking. Now this can be environmentally assisted cracking, such as sulfide stress cracking, or hydrogen embrittlement, where you would end up seeing a cracked coupling. Manufacturing was also pretty high in terms of a percentage here, and this is some transparency that Tenaris is providing, but also, again, this is also pipe not produced by Tenaris, just some information that we received from various operators who picked up a conversation with us after having a couple of issues, and that's about 18%. 14% was due to running issues, whether you're seeing cross-threading, no shoulders on connections, poor torque turn plots, and then it continues with some that let's say some percentages that are relatively small here: 9% for ductile overload, 8% for torque drag and fatigue, and this is let's say over torquing during running or seeing a fatigue failure due to let's say an extreme amount of cycles being generated as a result of having to rotate the casing to bottom. About 7% for corrosion, 5% for cementing issues. This includes poor placement of cement or just having let's say uncemented sections that might see trapped annular pressure. And then we also have wear, formation, movement, and others, making up about I want to say about 8%.
I think the most interesting thing for me on that is that 53% happens during stimulation, but I suspect that a lot of that damage occurred during the installation phase. So if you're not planning for wellbore instability, you're not planning for your hole cleaning plan, and you're not training your crews on how to run the casing, and it's normal in a horizontal well for the casing not to want to go to bottom.
Sure.
Gravity does that to us, and if you don't have that pre-planned and taken into account for, then somebody's going to get cowboy with it and start working that pipe. Yeah, and they will get it to bottom. And I mean, there's a famous picture that goes around that shows a wellhead upside down in the cab of a fracking truck because it was buttress pipe, and they worked the crap out of it, and they got it to bottom, and then they hit it with 15,000 psi, and shockingly, it blew up. So,
yeah,
I think another interesting thing in that slide is that more than half of the casing failures are the connection, not the pipe body.
Yeah.
Because when we focus on casing design, we go through all these different load tests and whatnot, and we come up with, and is it sour service or not? And we come up with a grade and a tensile strength and everything is focused on the pipe body.
And we just use whatever
and then
connections
when we select a connection, it's just like, well, what kind of torque do I need to get it down? Does this connection provide that torque? Done. That's 90% of the engineering into
typically when we pick up conversations with operators and drilling engineers who are involved in the design phase, and we start asking questions, it's like, hey, I only took a look at the data sheet, and it says that it can perform in terms of internal pressure capabilities, tension capabilities, and then I have enough torque. But as Jorge presented, there's a lot more that goes into selecting a connection. If you want to have a little bit more of a guarantee in the performance of the connection, you might want to opt for one that's been tested, that's demonstrated that it can go through the various stages, such as installation, stimulation, and production under very demanding conditions. So that's something, again, kind of tying it back to connections, but we've also, and I'm going to go pretty quick through some of these slides. I'll finish it up on this slide. So there are all types of failures that can occur. A couple that I want to highlight here include crack couplings, because it made up a significant percentage of the failures that we have in our database. And this can be minimized by controlling a couple of factors that contribute to crack couplings. The first one being, and not necessarily one that you can control, is the presence of let's say acidic gases, whether it's through production or the introduction of acid in preparation for a stimulation job. Then you also have material that is susceptible to cracking. Now, working with the higher yield strength material such as P110, you're going to have material in the well that's susceptible unless it's designed specifically to resist cracking. And that's a whole nother conversation that we can have. But another element there is the stresses. And with API connections and even buttress compatible connections, we're finding that a significant stress level is reached just by making up the connections. And if we compare those stresses to, let's say, a wedge connection where it distributes the stresses pretty good along the entire length of the connection, we find that a wedge connection would be more likely, or let's say less likely, to crack in comparison to a API buttress or even a buttress compatible connection. And we also have pin nose restrictions, and this is just a matter of working casing and not necessarily working the casing as it should be worked. For instance, if you're stalling out continuously during washing and reaming operations, you may see uncontrolled makeups occur downhole where Imagine stalling at surface and the momentum of the pipe is still being carried downhole with the addition of some compression due to bending. You are going to see the possibility of a scenario that ends up with restrictions downhole at the time of stimulation. You're having to go in there and mill through them in order to have the ID that you need in order to complete these wells. Another point is fatigue failures. You need to understand the fatigue limits of your connections. If your connections have, let's say, if you really don't understand the fatigue limits of your connections and you start going through operations where you generate a high accumulation of fatigue damage, you can potentially see a failure of a connection. For instance, with operators looking at rotation while cementing or longer laterals requiring a significantly longer period of rotation, you can end up accumulating a significant amount of fatigue and therefore putting you in a poor position.
So that's understanding the fatigue limits of the casing, but also understanding the fatigue environment. And
exactly.
If we're only taking surveys every 90 feet, then you don't really have a good understanding of what the true dogleg severity is and how bad those bending stresses and fatigue stresses can be.
That's a good point, because if you're, let's say we're evaluating the anticipated fatigue for a specific trip-in schedule where an operator thinks that they'll be able to run under specific parameters and then possibly rotate off bottom for rotation while cementing. If you don't necessarily understand that there might be a presence of a micro dogleg, let's say a 25 instead of a 18 that is picked up in the 90-foot survey, your estimation of fatigue is going to be severely off in comparison to if you really considered these micro doglegs.
And then you blame the casing manufacturer.
It's also standard.
I laugh because we've heard it. So
we have gone over our 1 hour, but there are a couple of topics that I think are really important that we still have not touched on. So I still want to cover those before we talk about them, before we sign off. One of them is operating torque versus makeup torque. We need to cover that. The other thing is, because we had a question in the chat that is really important also, it's because it's something that we recommend on a regular basis, is the risk of floating and rotating. So
Sure.
You're rotating pipe that's basically dry reaming.
right.
And the risk of causing a casing failure, because that's something that we recommend. So I know you have in your presentation, maybe show the
Sure.
picture of the damaged pipe, and then let's talk a little bit about the risk of rotating dry without pumping.
Sure. So one of the big issues there is that because
Rodney,
you're not,
can you go to the slides real
because
quick?
you're
So you
not
have the picture.
circulating, you're not able to change the temperatures that are being seen at specific points within the trajectory, within the string, that might be subjected to higher stresses. So imagine rotating and subjecting a connection or a segment of the pipe to an extreme dog leg. It's almost as if you're bending a paper clip, and if you bend it just a few times, you'll see that the paper clip ends up getting a little bit warm. A very similar thing is occurring downhole, where you start generating this heat, and because you're not circulating, the heat isn't dissipating. It's just being concentrated in a specific location, and that heat can get so high that you end up changing the mechanical properties of the pipe. In this case, we saw an operator who basically floated and rotated at the same time for an extended period. And typically this is isolated to extended periods of rotation, and we can see the necking develop in the pipe body.
I would say it's not just the extended period, because floating and rotating is usually a slower operation, so it tends to lead to longer running times, and if you're rotating, it might take a while also. I think the really important thing is to show that this is a valid concern.
It's a risk. It's a risk.
It is a valid risk, but the way that you mitigate this is by not staying, because like the really important thing that you pointed out is the cyclical fatigue, right?
Exactly.
So you're only going to have accumulated cyclical fatigue is if you are, because it's associated with if you're sitting vertically, sorry, no dog legs, if it's just a straight section and you rotate it, I would say the risk there is pretty minimal.
Exactly.
Usually it's rotating through a bend where you end up accumulating a lot more.
And I've seen a few examples of that where it's not intentional, but we're running casing and then there's something happens on surface and we got to stop for, maybe it's a fire drill or something like that. We got to stop for 5 or 10 minutes or 20 minutes. And there's this thing that we can never leave pipe static in the well. So you just let it rotate and then you forget, you move on, and 10 minutes turns into an hour and boom, it breaks. And so you have to think about that as well. Like, be prepared for.
Right. It's all about your ROP or your rate of penetration in this case, because if you're able to continue to progress, the chances of you heat checking your pipe are pretty low.
Right.
But if you're continuously in the same spot, and again, that kind of goes back to the idea of planning and ensuring that you have enough torque, ensuring that you understand what it's going to take in order to reach bottom. And if you don't really understand that and you end up in a difficult spot where you're not sure as to how you're going to progress, but you're continuously rotating, you are going to possibly see this type of failure.
So the short answer to the question that came in chat is, it is a valid concern. It is a risk. But the mitigation of that is to not rotate while stationary. Just make sure that the pipe is constantly moving, so you're not accumulating fatigue over certain joints.
Do your homework and take care of your well and make sure you're ready for the job.
Yeah.
Yep.
And if for whatever reason you can't get down to bottom and you're going to spend a lot of time trying to get the pipe free, then at that point it's probably worth breaking your either filling the casing and start circulating at that point, or if you're running mud over air, to break the hydraulic seal and fill up the casing, maybe start circulating at that point.
And that's kind of the perils of ERD drilling, that some casing runs are one-way trips, and sometimes we're floating casing, and if you can't float it and you have to circulate, the casing's not going anywhere. So it just highlights the need for good hole condition and focusing on that.
Right. Because a lot of times, if you do fill up your casing, you're not going to be able to rotate
it.
So rotating it stationary is no longer a concern, because you can't rotate it because the torque goes up so high.
We've seen operators select a 400 series connection as a plan B. The intention is to float and reach bottom without having to rotate. And in some cases, everything works out. You don't need to rotate. But for that one instance where you do end up having to rotate, if you have enough torque, you can possibly work your way down to bottom.
I do have another question about the published fatigue, or is it published some of these casing failures? Those casing failure, is that internally, or is it published material?
It's published material. We published a paper through ERTEC last year, and it was presented last year during the virtual ERTEC event. In fact, the paper number for those failure statistics is ERTEC 2581. The paper is titled "Maximizing Reliability, Well Integrity Statistics, and Risk Reduction Strategies."
Is that in one of the papers that you had?
Yeah, so if we put up the slide, we can see the papers that we think are able to kind of tie this presentation all together. We have two papers that we published regarding the development of connections, the 461 as well as the Wedge 441. And then, again, the final paper on this list is the paper that includes all of the statistics regarding failures and also risk reduction strategies. So some of the things that we discuss here in terms of how to mitigate these failures, or how to minimize the risk of these failures, are discussed in detail.
Okay, excellent. And then the last thing that I want to touch on before we leave is the wedge connection is one of the few connections where the published torque ratings on the spec sheet can be very confusing to people. There's minimum, maximum, optimal makeup torques, and then there's another line that says operating torque and then yield torque, and usually that
and buck-on torque.
Yeah,
sure.
So can we go through those, because a lot of people are uncomfortable. Whatever you make up something at surface, that's what they're going to set the stall limit to, and they don't want to exceed whatever they make it up to. Yeah. So if you have an operating torque that's higher than your makeup torque, well, then why even have a maximum makeup torque? Should you make it up to your operating torque? And so maybe discuss that in a little bit more detail.
Okay. So the buck-on torques are torques that are specific to what we are applying at the mill, and this is specific to threaded and coupled connections only. You won't see a buck-on torque for an integral connection. The makeup torques, the minimum, optimum, and maximum makeup torques, are torque values that we believe fully engage the threads and provide a level of sealability that we see in this testing, and also full structural performance in terms of tension, and also let's say structural performance of internal pressure capacity, external pressure capacity, etc. Then we have the operating torque, which is a torque value that you can consider it as a value that has an applied safety factor to it, because it's a certain percentage below the yield torque, and the operating torque is the value that Tenaris is comfortable with the operator using as their let's say their dump value on the CRT, etc. If the need comes for them to have to rotate. So if you're rotating casing and you find that maybe the maximum torque isn't sufficient, we are okay with advising to move up to the operating torque, and typically that's a significant increase over the maximum makeup torque. Now, it's interesting that you bring up the point of setting a limit at maximum torque, and we've seen this with a lot of operators out there, and we think that this is an issue. In fact, we ask for operators to set the dump valve limit to operating torque in order to just start working with the maximum torque that the connection can withstand. And the reason why we ask for this is because if you start off with, I don't know, 5,000, 8,000, 10,000 foot-pounds of torque, you are more than likely going to see stalling while you're rotating. And if you're seeing the stalling, you might develop restrictions downhole as a result of these dynamic loads that are developing downhole. So if you start off with certain rotation parameters, your operating torque as your dump limit, rotating at 40 RPM as opposed to rotating at 5, 10, where you're not necessarily seeing a benefit from the rotation, then we believe that...
Can you repeat that one more time?
Sure.
Because that's one of the biggest struggles.
For you guys too? Because
for everybody. People are very
rotating.
Uncomfortable about rotating
exactly
casing at decent speeds.
Yep.
Like it freaks everybody out.
Yeah, and the funny thing is that we've seen pretty high levels of RPM for drilling with casing applications. So, and the 400 series connections are also developed for use in drilling with casing. So if we are advising for specific rotation parameters in drilling with casing operations, we are comfortable with seeing 40 RPM during a washing and reaming operation. But you're right, there's a lot of operators who are very hesitant to start moving up to these higher values, the higher RPM values, the higher operating or torque values, which if you start off in using these higher values, you're more than likely going to be able to operate without seeing the risk of issues that can develop.
Even if it's in the plan, there's still like this air of caution. Like, okay, if we have to, we'll go up to 40 and we'll go up to operating torque. But like you said, we're going to set the stall limit at 10,000 foot-pounds now, and we'll rotate at 5 RPM and see if that works. And then it doesn't work, and people give up on it. Yeah. So I mean, that's why training comes in, so that you don't have somebody on the rig.
And how do you define what's working, right?
Yeah.
If rotating 5 RPM is successful at you moving down at like 10 foot a minute or 5 foot a minute, technically it's successful. But if you rotate at, but what we're talking about is the cyclical fatigue part of it, right? Yeah. So if you're moving really slow, then you're accumulating more cycles. And so even though a lot of, we don't do stuff that's intentionally stupid, right? I do believe that. I think
we don't do stuff like we don't always, we put it in the drilling program, but we don't always define on the day we're doing this, who's going to be the one to say what rotary speed are we going to use.
Right.
And so some crusty old tool pusher is going to be the one who shouts the loudest and intimidate everyone into doing what he wants to do.
Yeah. I mean, it's
unfortunate, but it happens.
the people tend to have good intentions, and they're like, well, why rotate at 40 RPM? Because 5 RPM is safer.
Yeah.
So it's good intentions with bad outcomes.
Yeah.
Because it's just a misunderstanding what's happening. Where actually rotating faster, which is the thing that you have the fear the most, is actually the safest thing to do.
And most efficient.
And most efficient.
Exactly.
So that's interesting.
That's cool.
We did have one more question about 9 and 5/8 casing. I know this is not the topic of this because we don't have 9 and 5/8 high angle in unconventional. But I guess everything that we talked about in these casing sizes transfers to the 9 5/8 also.
Not necessarily.
Not necessarily.
For instance, these 400 series connections are not available in 9 and 5/8, at least not yet. If there's an operator out there that's interested, we can start discussions and see if maybe one of these connections can be transferred over to the higher.
So the 9 5/8, is that still the 5 series then, or is the 6 series?
It's 5 series, and I think maybe some 6 series are available. Jorge can possibly confirm that.
Yeah, there are some 600 series for that too.
But predominantly the 5 series then, for the 9 5/8.
Yeah, 500 series is definitely 500 series is the one we would go with.
One thing that is different, just for everybody listening, one thing that's very different between smaller casing size and larger casing size is the benefit from flotation is much more significant because you're displacing a lot more fluid. The other thing is with that larger casing size, it tends to generate a lot more torque because torque is your normal force times your effective radius. So with your effective radius being the casing is heavier for one, and the effective radius is larger, so you tend to see much higher torques with 9 5/8. So it almost forces you to float, which adds a whole lot of other complexities.
I think maybe related to that question is your page with the statistics of casing failures. Would that be similar with 9 and 5/8 compared to 4.5 inch, the mechanisms and the types of failures?
I think the distribution in terms of percentages would be very different. And the reason why I say that is because you're not going through stimulation with 9 and 5/8 inch. You're not producing through 9 and 5/8 inch. So most of it would probably be isolated to the installation and possibly some additional characteristics if we're talking about cement and other things that can possibly have.
Is there a difference between big pipe and small pipe in terms of sensitivity to manufacturing issues, or is one easier to make than others?
That's a good question, and I'll have to follow up with you guys. I've never asked the mills that question to get an answer, but I don't know. Maybe Jorge, do you with your time in Tenaris, have you been curious enough to ask that question?
No, I've never asked that.
Well, thank you.
Sure.
Yeah.
Thank you, Lee. Thank you, Jorge, for stopping by. We've already gone 22 minutes past our time.
Keep going.
Hour. Yeah, we could. We could definitely keep going. I love talking about this stuff. One thing that I would like to point out. So I believe this is the first time we've brought in another service company or. Oh, SDI. That's right. So we have brought somebody else. We try to keep all the conversations technical, which I think we did here. I also don't want to, like I said, the wedge thread is the Lamborghini of connections. I don't mean to poo-poo or like downplay other connections or your competition. I'm not trying to push Tenaris over anybody else. I think they have a premium. I do think they have a premium product, but there's a lot of people that have really good products also. So I
think there's enough space for many connections to be used in various applications.
Right. So I hope you enjoyed this conversation. Again, we'll continue to try to offer it the third Friday of every month. So join us next month. Smash the like button. Oh, next month is the Spanish-speaking one. Okay, yes. Oh. Yeah, so next month will be we'll have it'll be what's the topic again? Oh, well, we'll figure it out. We'll figure it out. Yeah. So. Yeah, I think it's going to be a more of a case study similar to what we did in the Marcellus, but something more applicable to South America. And it'll be in Spanish. We'll have one of our senior drilling engineers, Julio Palacio, will be on here. Walid, who is he speaks about 10 different languages. He's a geomechanics guy. He'll be on here also, I believe, with him. That's what will happen next month. Hope you enjoyed this. If you do have any questions, one thing that I'll ask, there was another question that I said that you can just hop in and answer it in chat, and maybe go into the chat and share your contact details.
Sure.
In the chat on the live feed for people that want to contact you. But thank you very much for the guys that spent close to 90 minutes with us.
Yeah,
we
thank you
appreciate
guys.
it.
Yep.
That was interesting.
It was great.
Thank you very much.
Thank
for
you
the
guys.
invitation.
Enjoy the rest of your
Pleasure.
day. Thanks. Take care.
You